Hello, and welcome to the last section of Math 068, Section 20, Finding P-Values on a Graphing Calculator. In fact, we've already covered the majority of this material. I'm adjusting my camera a little bit here so we can get everything here. We've already covered a lot of material because I stepped ahead a little bit, if you will, on Chapter 19, knowing what was coming in Chapter 20, and I wanted to get started because I had people asking me, show me how to find the p-value. Show me how to find the p-value. So that's what we in fact did. So let's go over kind of quick, and I will tell you I've already pre-filled out the notes because there was a lot of writing involved, and I will talk through the entire thing and pause as you need to. Okay. So first of all, our parameters of interest. One, are we dealing with a mean, a t-distribution? And in that t-distribution, remember we're using TCDF. If we're actually finding an endpoint, so a data value, we are giving already a parameter, a p-value. We're given an area, and we want to find something. We're going to use inverse t. And oppositely over here, when we're talking proportions, in proportions, we always use the normal CDF to find the area, and we use the inverse normal CDF to find the endpoints. Okay, and here's your commands above each one of these boxes. And these commands are to live by and to die by when you're doing this work. Okay. A couple notes at the bottom is that, first of all, obviously that second vars brings up this calculation on a graphing calculator. So if we use second vars, we will get to these choices of these screens. And it says, recall that for the left and the right test, we need to use infinity as a lower and upper bound. So when we talk about the number farthest to the left or the number farthest to the right, we're using infinity. Well, we don't really have an infinity marker in our calculator, but what we do have is a -1 times 10 to the 99. That's a -1 with 99 zeros on the right side of it. That's a pretty small number, folks. And that's over here somewhere, infinitely to the left. And the only opposite deal is if we're using on the right-hand side one. If we have a right bound, we're going to use a +1 to that same 1099. If we have a right tail test, we want to use +1. If we have a left tail test, we want to use -1. If we have a test that's in between two numbers, we won't use either one of these because we're not going to infinity. So let's look at the first example that we have. This is student exercise number 1. And like I said, I pre-filled them out, so try not to look ahead at it too much, but try to stay with me where I am. So it says we have h sub o, and we know we have a proportion. So first of all, we know that a proportion is going to be a z-value. It's always a z-test when we're testing for a proportion. When it's a mean, then it's a t-value. We know that the alternative is p is greater than 0.5, and using the sample results, p hat, so here's our statistic, is 0.57, and we know we have n values at 40. So I set up my formula. Z is equal to p hat minus p sub nothing going on, divided by the root of p of, again, the null, nothing going on, at 1 minus p sub o divided by n. My values are p hat, 0.57, the null, 0.5, the null again, 1 minus the null, and divided by n, which was 40. When we put that into a calculator properly, we get a z value of 0.89. So my ultimate goal here is to find the p-value, though, not the z, but to find the actual proportion of that tail to the right-hand side, which contains all of the area of 0.89 or greater. How do I know or greater? It's a positive number, 0.89, and the test said that we were running to the greater side. So I know it's a right tail test. You might want to make that notation when you're doing your work that you're testing at a right tail. So I take my calculator now, and I do that in second vars. Second vars is where I go. Because it's a z value, I go to normal CDF. I enter my first data point, 0.89. Remember, that's my left side number. Comma. I use that right side infinity marker, 1E99. I always add a 0 and a 1 because I know it's a 0 distributed on 1. You do not have to enter these. I like to put them in there for clarification. And when I hit the button, I get a p-value of 0.187, approximately 18.7% of the data is contained from the point 0.89 to the right-hand side. It's important to know what we're finding. We're finding the area which is as extreme as or more extreme than 0.89 on a standard normal distribution. Student exercise 2. Now, if you look here now, immediately it's a mu value. If it's a mu value, it's a t-test. So we have mu at 120, alternative less than, left test. So you might want to make a mark here, left test. Here's your sample, 112.3. Here's your standard deviation, and here's your n value. First of all, important to mark down right now, degrees of freedom are always one smaller than the smallest set. The smallest, we only have one set, so it's the degrees of freedom are 99. We need degrees of freedom for a t-test. My formula, t for a single mean, x bar minus mu abot divided by standard deviation divided by the root of n. We simply plug our values in, and we hit the button on the calculator. Notice it's a negative 4184. It should be a negative 4184 because we're left tail testing. So we're going left in area from a negative 4.184. Now when I go to my second vars, I don't choose normal CDF, I choose TCDF because I'm in a t-test. T-test, TCDF. I put in the extreme left number. Well, remember, since this is a left tail test, it's a negative infinity, comma, my maximum number I'm going to get to is negative 4184. And comma, in here, we don't put in zeros and ones, we put in degrees of freedom, and the degrees of freedom are 99. We hit the button, and we get 3.102 approximately, and you get this E negative 5. Remember what that really means is that's a 3102. So I took the decimal point right here. And because it's a negative 5, it means move the decimal 5 times this way. Well, that means 1 to here, 1, 2, 3, 4. That's the true decimal, and it is very, very small. You would reject this p-value in all circumstances, because if we even rounded to 3 decimals, it's a 0. Incredibly small. Know your scientific notation when it pops out in your calculator means something like this. Student exercise 3. I have mu 1 and mu 2. So again, bells should start going off, t-test. But there's 2 values here, so there's 2 mean values, okay? Well, then the formula I want to use is this beastly formula right here that uses a t-test for means, and it's the difference in 2 means. It also is a two-tail test. I see that from right here. I have it circled, two-tail test. I also have to figure out my degrees of freedom. And if I look at this n value at 100 and I look at this n value of 80, then my degrees of freedom in my problem are one smaller than the smallest value, which will be 79. I haven't done a single bit of calculating other than reading everything from the problem so far. So I fill in my values. I take my x1 and x2, I subtract my null, I take my first standard deviation and I square it, divided by the set of n. I take my second standard deviation and square it, divided by the set of n. Practice doing this. When I calculate that t number, negative 1.569, I'm on the left side, and I have to realize that this is the left side number. I know it's left because it's negative. But remember, this is a two-tail test. So what, in essence, we're going to do is we're going to calculate the area to the left because of this number right here. And then we're going to multiply it by 2 because remember, a two-tail says that there's also area over here. So I'm going to go to my calculator and I'm going to do TCDF. I'm going to test it left, infinity, up to the left number. Again, I can't stress that enough. I know I'm on the left, not the right. I put in the degrees of freedom, and I just let my calculator roll at times 2. I don't even care about this number. I want to multiply by 2 outside the parenthesis, and I get a p-value of 0.121. imperative that you know we're on a two-tailed test. You got a negative number. Had you gotten a positive number, you would have tested from the positive number to positive infinity, and you still would have multiplied by 2 to get the other side. Number 4. They just keep getting better, don't they? Look at the size of this thing. Again, now we have a proportion 1 and a proportion 2. So we have 2 proportions and a 2-tail. So in the first 2 lines here, I have some great information. I don't need to worry about n size as far as my degrees of freedom go because I'm in a proportion. My z-test is P1 minus P2 minus the null divided by the root of, remember, pooled proportion times 1 minus pool proportion divided by n. Same thing here, but divided by n2. My pooled proportion, remember, is the statistic times the number of n. So the decimal times how many n plus the other decimal times the other n divided by the sum of the n's. My first statistic was 0.4, p-hat, times 382 things plus 0.6 for p-hat 2 times 192 things, all in the numerator, divided by the sum of the 2 n sets. So we're pooling together all of the people and the percent of each of those people. P-hat, 134 over 287. On the last video in 19, you saw me use this actual fraction, but this time I'm going to use the decimal. I take that p-hat value, and I load that p-hat value into all the pooled proportion places. I keep the 0.4 minus the 0.6 in order, p-hat 1 minus p-hat 2. I do all this in my calculator, and I get z equal negative 4.531. Again, I have to remember, this is a two-tailed test, and this is only one side of the two-tailed test, and it happens to be the left because of that negative number. I do normal CDF, negative infinity, comma, my negative value, which is my left side test, comma 0, comma 1. Remember, I just like to do that. Parenthesis close, times 2 because of the two-tailed test design. I hit the button, and I get a p-value of 587 E6. We already had this discussion. E6 means take this decimal, move it 6 positions to the left, and you've got yourself one crazy small p-value. You would reject the null on every value that's going on here. Exercise 5. Notice right away we have a single proportion. Nice, because the formula gets smaller. We're left tail. So we're going to use the formula that we've used before. We're going to fill out for z. We're going to take the sample statistic, 2, 1. We're going to take the null, 0.3. We're going to divide by the null, multiplied by 1 minus the null, and we're going to divide it by the set of 200. We're going to get a z value of negative 2778. We're going to return to normal CDF. We're going to do negative infinity. Again, left tail, negative infinity, comma, statistic, z, 0, 1, and I get a p-value of 0.003. I do not multiply by 2. It's a single side. It's a left tail. Only when this is not equal do you multiply by 2. I have mu value here, 2 of them. So I'm right back at that mu change or that mu calculation for 2 means. We've done this one before. So you can see I filled in 56 for my first sample and 51 for my second sample. My standard deviations get squared, divided by n. Separate standard deviation squared, divided by n. I take all that and I get a t-value of 2.699. Have you already guessed at what the degrees of freedom will be? Degrees of freedom will have nothing to do with sorry, I stopped there for a second. I had a little bit of smudginess going on the paper. I couldn't even read it. Again, get back to my degrees of freedom. I have 2 sets here, 40, and I have another set, 30. Mine looked like a 39. I had to fix it because I was too messy here. We go to the smaller set, and the smaller set is 29. I put in the values. TCDF, I get p-value of 0.005. Last two. I'm getting close. I have a mu value, a single mu of 4, and I have a two-tail test. So I go to my t distribution, and my t distribution says that I should take 4.8 as my x bar minus my mu of 4. I should divide all of that by my standard deviation divided by the root of my n values. I also know right now, because my n is 15, that my degrees of freedom are 14. I get a t distribution of positive 1.347. Now remember, this is a two-tail test, so this is the right side tail. And I know it's the right side tail because it's positive. So I'm going to calculate based on this as being the low number, this is the infinity to the right, this is the degrees of freedom, and I'll multiply the answer by 2, and I'll get a p-value of 0.199. Not very significant. We really would not be rejecting this. That's a lot of area. My last one is similar to my previous. This is my z-test of two populations, so I will need a pooled proportion. I'll start with my pool proportion. It's 0.48 times 75 things plus 0.28 times 75 things, and the sum of those two 75s is 150. My pooled proportion is 0.38. I load 0.38 into my z value over here. I take my test statistics and subtract them. I take my pooled proportion minus times 1 minus the pooled proportion on both counts. And because both had a 75 set, they both look identical to each other with an addition sign in the middle. This is a single tail test to the right. 2.53 gets loaded into the normal CDF, going to infinity, distributed on a 0, 1, and I get a p-value of 0.006. I hope this has been informative for you, and that ends section 20. Welcome to the end of Math 068.